Hi everybody. In today's video, we're going to look at trigonometric substitution. This is slightly different from the basic substitution we looked at previously, but there are some similar ideas in terms of having to replace the integrand and the differential within the integral. And so let's take a look at that. Most trigonometric substitution problems center around variations on the Pythagorean identity from trigonometry, which says that sine squared of theta plus cosine squared of theta equals 1. Okay. So in general, if I have a piece of my integrand that looks like a squared minus x squared, so a is a constant and x is a variable, then my substitution will be x equals a sine theta, and we can then simplify this by saying a squared minus a squared sine squared theta is a squared cosine squared theta. So the x gets replaced with a sine theta, and then when we simplify the a squared x squared, it becomes a perfect square. And this is really why, or one of the reasons why, we want to use trigonometric substitution. It changes something that is a sum or a difference into something that is a perfect square. And that frequently will allow us to simplify our integrand with some cancellation. Okay. If our integrand looks like a squared plus x squared, then our substitution will be x equals a tangent theta, okay? And when I replace x with a tangent theta, I get a squared plus a squared tangent squared because I replaced the x. And again, because of the Pythagorean identity, this could be simplified to a squared secant squared. So we're changing this sum of squares into a perfect square. Finally, if something looks like x squared minus a squared, so it's the variable squared minus the constant squared, but it's still a difference of two squares, then I'm going to use the substitution x equals a secant theta. And when I make that substitution, when I replace the x with a secant theta, I get a squared secant squared minus a squared. And again, from the Pythagorean identity, from manipulating the Pythagorean identity, this simplifies to a squared tangent squared. And so we've changed a difference of two squares into a perfect square. So in every situation, in all three of these situations, we're using the trigonometric substitution to change either the difference of two squares or the sum of two squares into a perfect square, which will then allow us to make some simplifications. So let's look at an example of substitution where I replace x with sine theta. So looking at our integrand, I have 1 minus x squared, which we could think of as 1 squared minus x squared. So this matches the first example that we did. It matches the a squared minus x squared, where a equals 1. Okay, so I'm going to let x equal sine theta because I'm following the pattern that I outlined on the previous slide. That means that 1 minus the quantity x squared is 1 minus sine squared. But using the Pythagorean identity, that's cosine squared. So I've changed this difference of two squares into a perfect square. I also need to take care of the differential dx. The derivative of sine of x is, or sine of theta is cosine theta. So dx is cosine theta d theta. And now I can make some and then I also need to deal with my limits of integration because I'm doing a definite integral. So if x equals 0, that means I need sine theta to equal 0, and so theta equals 0. And if x is 1/2, that means the sine of theta is 1/2, and sine of theta is 1/2 if theta equals pi over 6, and that's 30 degrees. And that's one of those common identities that you should hopefully know. Okay, making all the substitutions. I replace the x equals 0 with theta is 0. I replace x is 1/2 with theta is pi over 6. the 1 minus x squared gets replaced with cosine squared. That way we've changed this difference of two squares into a perfect square. And finally, the dx, the differential for x, we come over here, and from this derivative that we took, we see that dx is cosine theta times d theta. Now, this is where we can start making some simplifications because I have a copy of cosine theta in the numerator and a couple copies of cosine theta in the denominator. I can cancel one of those. 1 over cosine theta is secant theta. And you could either work out what the antiderivative of secant theta is, or you can look it up, or maybe you have it memorized. It's relatively a relatively common antiderivative. And that will be the natural log of secant theta plus tangent theta. You do need to be careful that this quantity is positive. You don't want to try and take the natural log of a negative, not in this class at least. And then evaluating the definite integral between pi over 6 and 0. We get that this will be the natural log of 2 over root 3 plus 1 over root 3 minus the natural log of 1. But the natural log of 1 is 0, and the input here simplifies to root 3. And so the answer is natural log of root 3. Okay, so that's an example of trigonometric substitution. Generally, the idea with trigonometric substitution is we're turning a sum or difference of perfect squares into a single perfect square, because that will allow us to do some cancellation, which in turn allows us to evaluate our integral because we've simplified it in some way. We've been able to do some cancellation. Okay. In the next video, we're going to look at integration by parts. And so I will see you later for that.